Hello friends, today I am going to discuss about magic square which is even sized. I believe you remember I have already discussed about magic squares which was of odd size in an episode prior to this, and after I had created, there had been several demands from people wanting to know how to develop a magic square whose size is even. So here is this particular episode which is dedicated for magic squares which are having its dimension as an even number. So this is what we are going to discuss over here. Now let me be very clear. You cannot have a magic square of size 2 into 2. You cannot have this, a magic square of size 2 into 2. Before thinking too much about this, let me tell you, define what a magic square is. It is such a matrix whose sum of each row, column and diagonal are always equal and the elements are unique. So forget about creating a magic square of dimension 2 into 2. It is not possible to create. So we can try out with the remaining even numbers. That is 4 into 4, 6 into 6, then we have 8 into 8, then we have 10 into 10, then we have 12 into 12, and you can carry on, speaking about different even size magic squares. And among the sizes of a square matrix, you will find there are two categories. One which are multiples of 4. There are others which are not multiples of 4. There are matrices which are multiples of 4. Example, 4 into 4, then we have 8 into 8, then we have 12 into 12. So these are all examples of matrices whose dimensions or whose size is a multiple of 4. These are called doubly even magic squares. And then we also have those even sizes which are not multiples of 4. Example are 6 into 6, then we have 10 into 10, then we have 14 into 14. And this is categorized as singly even magic squares. So to generate a magic square whose size is even, we need to divide it into two different categories. That is one which is doubly even magic square, the other one is singly even magic square. So once you are able to categorize these two, it's pretty simple to develop a magic square of even size. And let me tell you that it may not be possible for you to get the entire logic in one go. You may have to go through the logic, or rather go through the video once or twice to grasp with the logic. So this is required you may be requiring to go through the video once or twice to grasp the logic. And the program is already there. The program source code can be found in my blog, which is already written below. So you can always download the source code from the blog which I have created for your easiness. So you can always download the source code, or you can write the source code after understanding the logic. The entire source code can be found and can be downloaded from my blog. The link is given below. And that's it. You can just see the demonstration how I am going to create a magic square. So for convenience, I have taken this blank 4 into 4 matrix. First of all, we are going to learn how to create a magic square for a 4 into 4 matrix. Of course, I am talking about doubly even matrix. That is the size which are multiples of 4. That is sizes 4, similarly 8, 12, all which are multiples of 4. So here I have a blank 4 into 4 matrix. The 0, 1, 2, 3, this represents the column indices, and 0, 1, 2, 3, this represents the row indices. So starting from 0, we have till 3 representing 4 elements, and similarly for the rows and columns we have the same indices. Now these are the coordinates for each of the cells, where the starting one The starting value represents the row and the second one represents the column. So 0, 0 represents 0th row, 0th column. Similarly, 1, 1 represents row 1, column 1. Similarly, 2, 2 represents row 2, column 2. This is particularly helpful when we are going to write the corresponding code associated with it. So first of all, what we are going to do is we are going to shade the areas of the blank matrix as shown in this image. You can see in this particular image, I have shaded this area, I have shaded this area, I have shaded this and this, this and this and this. So you can see the shaded portions in this particular blank matrix. Now first of all, what I am going to do is, wherever we have this shaded portion, we are going to insert numbers starting from 1 till 16. Remember, we are supposed to insert numbers from 1 to 16. That is, for 4 into 4 matrix, we'll be having numbers from 1 to 16. So we'll begin from here. So here what we are going to do is, we are going to insert 1. And now you see something very interesting we have over here. 2, 3, we are not going to write. However, we are going to write 4 out here. So 1, 2, 3. So we are writing only in the shaded portion. The non-shaded portion, we are just going to leave it blank. I'm going to tell you within a short while what we are going to do with that. So we'll carry on. 1, 2, 3 remains blank. 4 and then 5 again remains blank. And then we have 6. We have 7. And again 8 remains blank. 9 remains blank. Again we have 10. And then we have 11. Again 12 remains blank. Then we have 13. Again 14 and 15 remains blank. We have 16. So this is the first thing which we need to do. Next, what we are going to do is, we are going to write once again from 1 to 16, this time from lower end to the upper end. So what we are going to do, you can imagine over here 1, and this time we are just going to do the opposite. That is, wherever we have this blank spaces, that is the non-shaded areas, we are going to write the numbers starting from here. So 1, then we have, since this particular shaded portion is already taken, we are not going to write over here. So we'll write over here 2, then we write here 3, 4 is again taken, then we have 5, 6, 7 is again taken, 8, then again we have 9, 10, 11 is taken, so we'll write 12, 13 is taken, so we'll write 14, and here we are going to write 15. So now you see, we have a magic square over here. Now once again I have prepared a blank 8 into 8 matrix sheet, you can see over here, and once again I have written the column indices and the row indices, which currently will not be of any use. However, when we go for the programming part, we are going to use it. Now this time once again I will be showing you the shaded portion. Now this time look at the shading, slightly different from the 4 into 4 matrix. This time we have 2 cells at the upper left corner and 2 cells over here also. Along with that, 2 cells out here, 2 cells out here. Similarly, like that, we have 4 cells in 4 different corners. Now I'll tell you the logic behind this. What is actually happening is, you see, for a 4 into 4 matrix, let's once again get back to what we had done previously. Here you can see the shaded portions, and we had only 1 cell in each of this shaded portion. However, the symmetry is still the same. If you observe carefully, the symmetry is still the same. Here the symmetry is still the same. All the 4 corners we have the shaded portion, and even in the middle. So the symmetry is still the same. What we are trying to do is, since the size is 4, so what we do is 4 divided by 4. The answer we get is 1. So 1 means we are going to take just 1 cell from each of the row and column. So for the 4 quadrants, and wherever it ends, from there whatever the remaining quadrants are there in the middle, we are going to take that. Now the same logic can be applied for 8 into 8 matrix. Here what we are going to do is 8 will always divide by 4 because this is a doubly even magic square what we are trying to build. So 8 divided by 4, what we get is 2. So that means we are going to take 2 cells from the row and similarly 2 cells from the column for the 4 corners, and whatever happens to be in the remaining area in the middle, we are going to shade that entire portion. The same thing can be applied even for a 12 into 12 matrix. I have a shaded diagram for that too. So here what we are going to do is we are going to divide 12 divided by 4. So how much do we get? We get 3. So what we are going to do is we are going to take 3 cells from the row, 3 cells from the row and 3 cells from the column. That is how we get each of this 4 shaded areas at the 4 corners, and whatever is remaining in the middle, joining each of these shaded corners, we are going to shade that also. Now getting back to the 8 into 8 matrix, we are going to follow the same logic. That is, first of all, we will start writing in the shaded portion numbers sequentially from 1 to 64. Why 64? Because this is the 8 into 8 matrix. The maximum number which we can accommodate out here is 64. So we'll start from here. So we have 1, then 2, 3, 4, 5, 6 should be left. We have 7, 8, we are going to start again writing from 1 to 64, this time from bottom to top. So we'll start from here, just from the opposite end, wherever we started 1, 2, from the bottom but at the reverse order. We went from left to right, so this time from right to left but from the bottom corner. So we will begin from here. So 1, 2, again left because these spaces are already occupied. So we have 3, 4, so this time, once again, what do we find? We find the magic square, and the sum of each row, column and diagonals are all same. Now, look at this program which I have written for the doubly even magic square which we are going to generate. I have just used the BlueJ environment because of its simplicity. It doesn't matter. In whichever environment you write, ultimately you will be using the same logic. Here simply I have made a display function to display the matrix. This you could have written it in the same function where we are generating it. So this particular function is basically, I'm going to highlight this, it will be easier. This particular function is actually going to display the two-dimensional matrix. And this is the function which I was talking about, which is responsible for, this is the function which is responsible for generating the magic square, this particular function. Now here, what we are having out here, you need to check out very carefully. You can also see this program in the blog, the link of which is given below this video. You can find the link over there. You must have also seen during the opening page when the video had loaded the name of the blog. So you can get the source code as well from my blog. Now let's see what is it talking about. First of all, I accept the size of the matrix of the magic square as parameter. Here I am not checking whether it is a doubly even number or not, that is whether it is a multiple of 4 or not. You can check it to make it more flexible, this particular program. Here I assume the user is going to insert a correct number over here, and then what I do is I'm running a loop from 0 till n and j also 0 to n. This I have mentioned earlier to get all the coordinates starting from 0 0, that is 0 0 0 1 0 2 0 3, which I had already talked before. And here I have taken the variable p, which is initialized with 1, to represent the number which I am going to insert over here, and the value of p is being incremented out here. You can see over there p plus plus. The p plus plus is going to increment the value of p with every iteration. And here you see I have taken out this m, where m is n divided by 4. That is the size of the matrix divided by 4. This will give me the number of cells which I have to leave from the 4 corners, which will act as the shaded portion. Remember, which I had already talked before. Now you see for the upper left corner, I have given the condition I is less than m and j is less than m, which I have already explained before. And whenever this condition is there, I am inserting the value of p, where p is starting from 1. Similarly, when n minus 1 minus I less than m, so this is the lower right corner. So the lower right corner, out there I am inserting same way the value of p. I can show you the figure once again over here. This is the figure. And here what do we have? Here we have for the lower left corner, where I have already discussed the condition, that is n minus 1 minus I should be less than m and j should be less than m. And upper right corner will be I should be less than m and n minus 1 minus j less than m. And this is the segment in the central part of the matrix, and all the conditions are ANDed together, that is I should be greater than equal to m and n minus 1 minus I should be greater than equal to m. Note that it's just the opposite of this, and all the conditions are ANDed over here. And still out here I am inserting p. And remember, if none of these conditions are satisfied, that means I am in the coordinate I and j is in which particular cell? It is in that particular cell which is unshaded. So out there what I am going to insert, that is n square plus 1 minus p. So that's the value which I am going to insert over there. So that is what I am doing over here. Ultimately, after generating this, I am going to display the matrix. Let's try running this particular program. Let me close it, and we are going to run this program. Okay, let me compile it first. Okay, it seems to be fine. Now I'll invoke the doubly even function and just checking whether this function works properly or not. We'll start with a 4 into 4 matrix. So there we have 4. Okay, now what we're going to do is we're going to check whether this particular program is working properly or not. Okay, we'll close this. Let me right click on it and we'll call the doubly even function. This particular function is going to generate the magic square. Okay, we'll begin with the 4 into 4 matrix. Let me pass 4 to the parameter, and yes, we got that. You can see over there we got 4 into 4 matrix, which is a magic square, and remember the sum of each row, column and diagonal is 34. Okay, well, what I'm going to do is now I'm going to try for 8 into 8 matrix. Remember, for a doubly even matrix, the size to be provided should always be a multiple of 4. There. So you can see for a 8 into 8 matrix, we have a magic square out here. Okay, we'll try for 12. That will be huge, although it's difficult to understand. And there you got it. Hope you understood the programs and the logic behind it. Isn't it simple? About such a even-sized magic square whose size is not a multiple of 4. Prior to this, we had talked about even sized magic squares which are multiples of 4. The examples were 4 into 4, 8 into 8, 12 into 12. This time we are going to discuss about magic squares which are of course whose size is even. However, they are not multiples of 4. Examples are 6 into 6, then we have 10 into 10, then we have 14 into 14. See that all are even sized matrix, however they are not multiples of 4. Prior to this we had already done for single. We are going to break the entire matrix into 4 separate quadrants. This is the first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. Now after doing this, what we do is, each of these quadrants you will find that it is an odd size matrix. For example, if you take a 6 into 6 matrix, this particular matrix will be a 3 into 3 matrix. Each of the quadrants will be a 3 into 3 matrix. If you take a 10 into 10 matrix, each of the quadrant will be a 5 into 5 matrix. Similarly, for a 14 into 14, it will be a 7 into 7 magic matrix for each one of this quadrant. Now what we are going to do is, for the first quadrant, we are going to find out the magic square with respect to the odd size. So if it is 3 into 3, we are going to first find the magic square for a 3 into 3 matrix, which we had already learned in our first video, where I had already taught you how to generate rather a magic square of odd size. If it is a 10 into 10 matrix, once again we are going to generate a magic square of size 5 into 5, and all these elements which we are going to generate, we are going to insert it into the first quadrant. Now whatever we generate, each of these elements, let it be A. Now for the second quadrant, what we are going to do is, second quadrant will be A plus Q square. Now the question arises, what is Q? Q is very simple. Q is actually half of the size of the matrix. Here the size of the matrix, if I assume it to be n, when I divide it by 2, that will give you the value of Q. So this part is A, that is whatever we get for each of the corresponding number from the first quadrant, add Q square to it. So if it is a 10 into 10 matrix, Q will be naturally 5. So add 25 to each of the corresponding elements which you are going to insert into the second quadrant. For the third quadrant, it will be A plus 2 into Q square. For the fourth quadrant, it will be A plus 3 into Q square. So this is what we are going to do for each one of these quadrants. And after you do this, what are we going to do? We are going to interchange all the elements which are shaded out here. You can see these are the shaded portions of the first quadrant. Note that I have divided into 4 quadrants. So therefore, for a 6 into 6 matrix, look at the way I am dividing the quadrants. So these are the 4 quadrants, and note that this is a 3 into 3 matrix, this is a 3 into 3 matrix, this is a 3 into 3 matrix, this is a 3 into 3 matrix. The coordinates are written as usual. I have written the row and column indices. Similarly, for a 10 into 10 matrix, you can see that these are the 4 quadrants. Look at the way I have already emboldened the lines, and yet I am drawing it once again. So here, for a 10 into 10 matrix, each of the quadrant is actually a combination of 5 into 5 matrix. So this is a 5 into 5 matrix, 5 into 5, this is 5 into 5, and this is 5 into 5 matrix. Similarly, for a 14 into 14 matrix, you can see again I divided into 4 quadrants, and each of the quadrants are a 7 into 7 matrix. Now after we divide this, and after we after we divide it into 4 groups, for the first quadrant we are going to generate a magic square of odd size. So this part will remain same, and the remaining quadrants, that is first, second, third and fourth, will be according to the given formula which I have already discussed over here. So for this, what did I write over here? A plus q squared. So what I'm going to do is, whatever number you have over here, add q squared to it. Remember what is q? Q is n by 2, where n is the size of the matrix. So that particular element, corresponding element, add q squared to it. Whatever the value is, you can write it over here. Similarly, this will be this plus q square. Similarly, this will be the third element plus q square. Like that, for the corresponding elements, you can insert all the numbers. The same thing you can do for the third and the fourth quadrant. And after you insert this, we have a big job to be done. What we are going to do is, we are going to start with the process of interchanging. Now, bit peculiar, but once you get it, it's easy. Now, first of all, which are the elements you are going to interchange? I'm going to show you. So here I am showing you a matrix, a 6 into 6 matrix, where certain cells are shaded. You can see there are 3 cells which are shaded in the first quadrant. What we need to do is, we need to interchange the corresponding element with the fourth quadrant. So 0, 0 should be interchanged with 3, 0, 1, 1 with 4, 1, and 2, 0 with 5, 0. Look at the pattern. A zigzag kind of a pattern. This is what we are going to do. Look at the pattern once again for a 10 into 10 matrix. Now look at it. We begin with this, and then in the middle again we skip one cell. You can see for a 3 into 3 matrix also we were skipping one cell and the shade was going here. So same thing we do it for a 10 into 10 matrix also. You see, why 2? The reason behind this is, why this time 2 rows we are shading this way, is because 10 divided by 2 is 5 and 5 divided by 2, I am talking about integer division. That means the result without the point, that is only the quotient, we get 2. That is why we are having only the first 2 rows this way, and the middle row should be shifted one cell to the right. So this way, and this process continue. You can see even for a 14 into 14 matrix, this is what happens. This time 14 divided by 2 is 7, and 7 divided by 2, integer division, we get 3. So there are 3 cells, 3 rows, and the middle row, one cell to the right, and again we continue this way. So each of these elements should be, corresponding elements should be interchanged. And note that, for the 6 into 6 matrix, once again I'm going to get it out. For a 6 into 6 matrix, we did not have any shading out here. This is because for the third and the fourth quadrant, we did not require any interchanging at all. However, for a 14 into 14 and a 10 into 10 matrix, that means all matrices which are greater than 6, we need to interchange. Actually, the shaded region, you can assume, how did it come? There are 2 columns which we are taking into account. So 1 less than that, that is 1. So this entire column of the third quadrant should be interchanged with all the elements of this particular column of the second quadrant. Similarly, for a 14 into 14 matrix, 3. So 3 minus 1, 2. So only 2 cells will be considered. So these 2 columns will be interchanged with these 2 columns. See how simple it is. And for a 6 into 6 matrix, there was only one particular column which was taken into consideration. So 1 minus 1 is 0. That is why we did not take any of this column from the second and the third quadrant. This is what happened. So let's begin. So before demonstrating, what we are going to do is, I'm going to take a 10 into 10 matrix and start generating it. You have to be patient with this because you need to understand the concepts very well. Otherwise, it's quite difficult to understand it. So try to understand the technique which is being involved out here. So first of all, in the first quadrant, what we are going to do is, we are going to generate a magic square of size 5 into 5, because this is a 5 into 5 matrix, an odd size matrix, and I believe you have seen my first video on magic square, which was basically on odd size matrix. So we are going to apply the same rule, whatever we had learned over there, and generate the 5 into 5 magic square for the first quadrant. So let's start with this. So this is 1 out here, 2, I'm not
telling you the logic behind this. Once again, you can always refer to the first video on magic square to understand how I am doing this. And ultimately 25. So all elements from 1 to 25 is inserted over here. Now what we are going to do is we are going to fill up the second quadrant. Remember what the second quadrant was. If the first quadrant is A, then the second quadrant is A plus Q square. I believe you remember. I talked about it just a while ago. And Q, remember, whatever is the size of the matrix, n divided by 2. In our case, it is 10 divided by 2, that's 5. So here, what is the first element in the first quadrant? We had 15. So 15 should be added to Q square. Now Q square is 25. So 15 plus 25 gives you 40. So the first element in the second quadrant will be 40. Similarly, you can do the remaining calculations and just writing this as fast as possible. Now what we are going to do is we are going to start filling up the third quadrant, that is this. Now what was this? As discussed earlier, this was A plus 2 into Q square. So once again we will start with the same process and we get 65, 88, and I am writing the numbers as fast as possible. Now for the fourth quadrant. Remember the fourth quadrant was A plus 3 into Q square. So we are going to write each of the elements now from here. So same way, 90 plus 83 . Now we are filled up, but still we have some work to be done. You can see all the elements are filled up over here, but still some work is still left with this. You can see all the numbers are filled up. Now remember the shaded portion and we need to interchange. So first of all, let me mark the shaded portion. So here since this is a 10 into 10 matrix, so 10 divided by 2 is 5 and 5 divided by 2 is 2. I am talking about integer division, that is integer only, that is only the quotient, that is Q divided by 2. So what we get is, for this case, 5 divided by 2, that is 2. I am talking about integer division. So which are the portions which we are going to interchange? So 2 columns will be involved, 2 rows and 2 columns out here, and the middle row will be slightly inside. You have seen this earlier, and again we'll continue with the same thing. So this entire box which have inserted enclosed all the elements over here should be interchanged with the elements in the fourth quadrant and in the same pattern enclosed numbers. So this is the first one and this is the next one, and again this is the next one. Now 2 minus 1, so we get 1. So this time we will be interchanging only one column from the extreme right. of the third quadrant with the second quadrant. So let's start with this. So to illustrate the interchange, once again I have taken a blank sheet and I'm going to show you how we do the interchanging part. So this time I have 15 and 8 to be interchanged with 90 and 83. So 90 and 83 comes here and 15 and 8 comes here. Similarly 16 and 14 with 91 and 89. So 91, 89 comes over here and 16 and 14 comes here. Similarly 20 and 13 to be interchanged with 95, 88. 95, 88, you can see at this particular indices 95, 88 comes, and out here comes 20 and 13. Similarly 321 with 78, 96. And finally 92 with 84, 77. And the remaining portions will remain exactly same. There is no change. We don't need to do anything with it. Now what I'm going to do is I'm going to interchange the elements of the last column in the third quadrant with the elements of the last column of the second quadrant. So same way. So 67, 42. So we write over here 42 and write here 67. Then 73, 48. So 48 comes here and 73 comes here. Next we have 29 and 54. 29 comes here, 54 comes here. 35 and 60. So 35 out here and 60 out here. 36 and 61. And the rest of the elements will remain as it is, whatever is written over here. And thus we have created a 10 into 10 magic square. You can see over here. Isn't that tedious, I believe? Now we are going to see the program associated with this. Now basically this particular program consists of three functions: display, which will display the matrix, and here we have a function odd magic. You can see over here odd magic. I'll just enlarge it for you to understand it. So this particular function odd magic is responsible for generating a magic square whose size is odd. And this is a topic which I've already discussed in my first video on magic square. If you haven't gone through it, please go through it to understand it. It's pretty simple to understand compared to whatever you are learning now. And then comes the real function which is going to create the doubly even magic square. So here what I'm doing is I'm taking the size of the matrix, declaring the array, and here I'm calling the odd magic function which is responsible for creating a magic square for an odd size matrix, and this will be used for filling up the first quadrant. So this odd magic function will be invoked, and here what I'm doing is I'm going to insert elements into the first quadrant. So this is what we have done it to refer to the working which we had already done over here. Remember, we had already done over here. So this was our first quadrant, and in this first quadrant what we did was we generated a magic square. So this is what is going to happen, and then comes the filling up of the remaining quadrants. This is done in these two loops. So here you can see what I have done is Q I have already found out, that is n divided by 2. So each of this, that is I am filling up the second quadrant over here. Second quadrant, I believe you remember, this is the second quadrant. So this is what is being done over here, that is filling up the elements of the second quadrant, which is the first quadrant plus q square. You can see over here first quadrant plus q square. This is for the third quadrant where we have the elements of the first quadrant, add 2q square to it, and lastly for the fourth quadrant each element of the first quadrant plus 3 into q square. So this is what I am doing out here. So all the filling up of the remaining quadrants are being done in these two loops. Now comes what we had done called the interchanging part. Now interchanging, I believe you remember that there were two phases of interchanging. Remember we had this on the left side panel and on the right hand side panel. So we had to interchange elements of the first quadrant with the fourth quadrant, and similarly for the third quadrant and the second quadrant. So this is what we are doing over here. This particular part is going to interchange elements of the first and the fourth quadrant. This is what we are doing over here. Pretty simple to understand. And here we are interchanging the second and the third quadrant. Even this is very simple to understand. And ultimately I am displaying the magic square. So this is how the entire thing works. I'll give you a demonstration also. And I'll call the doubly even matrix, and this time I'm going to pass it in. Click on OK. So this is the magic square which it generated. Similarly, I can go for a 14 into 14 matrix. Let's enter the size as 14. So this is for a 14 into 14 matrix. I can even go for a 30 into 30 matrix just for fun. There 30, and you see it's so big it doesn't fit on a single screen almost. You can see over here that's a magic square which is generated. Beautiful, isn't it? So here you can see a 30 into 30 magic square, beautifully created by Java. Anyway, I believe you understood the doubly even matrix.
Thank you. I believe you liked the generation of a magic square whose size is even. Once again, let me tell you, you may need to go through the video once or twice to get the logic completely, or to grasp the logic completely. You can always download the source code from my blog, which is given, whose link is given below. You can just go through this particular blog and download the source code. In fact, all the source code of my videos prior to this particular video can be found in my blog. You can always download the source code and enjoy generating magic squares, or you can make your own logic and start developing it. Thank you.